Everyone, welcome to Big Data Thoughts. Today we are going to look at two very important optimizers or execution engine, which is Photon, and try to understand what is different between Catalyst and Photon and what kind of performance benefits do we get while we use this. So let's get started. Before understanding what is Catalyst, what does it do, or what is Photon, let us first look at what are the bottlenecks that Spark has when it comes to performance, or what are the factors that impact Spark's performance. Then we would be able to appreciate the optimizers that Spark provides. So first of all, one of the biggest challenges that the big data landscape and doing real-time analytics over it is evolving day by day. So data growth over the past decades have grown exponentially. It is not linear, it is not really predictable. We know that data is growing at a tremendous speed. The format of data is it is in multiple formats. It's not just structured, it is structured, semi-structured, there is streaming data, and the overall expectations or the use cases that we had has shifted from batch to real time within seconds. So all of this put together, the explosion of growth, the variety, the velocity, the expectations, it is becoming complex for any technology to process that amount of data in real time. And that's where Spark came in, and as a distributed framework, it has been at the core of this whole shift, and it is able to process data, huge data at real time speed. But having said that, there are still challenges even with Spark that we need to be aware of. Now, traditionally, the Spark execution had some limitations. What are those? So there is a overhead of the JVM. So Spark runs on the JVM. Now, if we talk about Spark running on a JVM, it is nothing but a Java process, right, which is running in a JVM. It adds extra layers of abstractions. It is portable, it is flexible. That is the whole point of why Spark was designed that way. But it has its own overhead of adding abstraction, of incurring some overhead of garbage collection, which will result in delays. There is no explicit garbage collection that we have to do, but internally Spark is doing that. So there is a frequent object creation, destruction. All of this add to the cost of the Spark job, the runtime cost. And they become very, very significant when we are talking about billions of objects being processed. If it is a small application, very small data, it may not be noticeable. But when we are talking about huge amount of data and billions of objects getting created, destroyed, garbage collected, there are definitely overheads that using JVM is adding. Similarly, there are costs associated with the whole serialization and deserialization process. Now, what is serialization? We all know serialization is when you want to transfer data across the network, you need to convert it into bytes. Any object or any data that you have needs to be converted to bytes, which is serialization, and then it has to be again converted to the object, which is deserialization. So this is a mandatory thing that we have to do. There are different formats that you can choose for this serialization and deserialization to be really efficient, but no matter what, it is going to add some time. The default Java serialization is very slow, memory intensive. So now there are alternatives which are like cryo, etc., which will give you performance boost. But still there is an overhead or a time added because of serialization, deserialization. And when serialization occurs, it hinders the CPU efficiency, right? Because this process will utilize the CPU cache. And what will happen is, since the CPU cache locality is lost due to the scattered memory access, it is going to add to a overhead. So all in all, JVM adds to an overhead, and also serialization, deserialization adds to some amount of overhead. So these are the primary two limitations with Spark. Now let us understand what is the role that Catalyst does when we talk about optimizing Spark queries, and this is all done before execution. So in one of my videos I had spoken about what's the step, or what are the steps that happen when we submit a job. There are steps like logical plan creation, physical plan creation. These are all done before the execution, and that is when the catalyst optimizer's role comes in. Spark has introduced a catalyst optimizer to mitigate all these inefficiencies before the execution begins. Now, when a logical plan is created, what happens is the user query is converted into a high level representation of all the transformations that are written in the code. Once the logical plan is created, then the catalyst, which is an optimizer provided by Spark, comes into play. What will the catalyst do? The catalyst will apply optimization rules like predicate pushdown, constant folding of data, projection pruning. And what are these? These are basically done to reduce any computation overhead. If we take the example of predicate pushdown, what does it do? It's like a filter. So if you have filters applied to your data, it will try to do the filters first because that will reduce the amount of data. So these are some kind of rules that the catalyst optimizer itself does. So we definitely have to write optimized queries, but from Spark's side there is a built-in optimizer which also applies these rules. And once these are done, after the logical plan, the rules are applied, and then the physical plan selection happens, which will choose the most efficient strategy. When you create a logical plan and you apply rules, you have options of physical plans, and Spark selects the most efficient one. One of the example can be, instead of doing a broadcast join, it will choose to do a shuffle join, which will be more optimized. So a catalyst role is to optimize and it significantly improves the query planning, but still you cannot completely avoid JVM and serialization limitations. Right? Now let us talk about Photon. Why was Photon introduced? So we know Catalyst Optimizer is performing well in terms of optimization, but there are still limitations of JVM etc. that we spoke about. So then Spark came up with this new execution engine, which is Photon, which is built for speed. Now what does it do? What is Photon? Let's first understand that. So Photon is Databricks, and this was given by Databricks. As we all know, Spark has been, if I say, taken up by Databricks, and they have taken open source Spark, Apache Spark, and then added lot of things on top of that and made it very easy to use Spark. So Databricks has come up with a next generation C++ native vectorized execution engine. Now this is C++ based execution engine, and this is to make sure that Spark goes beyond the limitations of JVM that we just saw. And this is meant to optimize or maximize the efficiency for SQL and data frame workloads. The whole purpose is that it can avoid the limitations of JVM etc. and then give a blazing native speed, right? And the basic idea of building Photon was that it wanted to combine two things: the database style query processing along with Spark distributed model. So it's a best of both worlds. And how it is important for us to understand how is Photon bypassing the JVM inefficiencies that we spoke about. What is it doing extra? So the one basic thing is that Photon has been written in C++. So there is definitely no JVM overhead that we spoke about, right? And it avoids all those garbage collection steps, object overhead, serialization, taxes, all of that, because it is written in C++. As it is a vectorized execution, which means that it processes data in batches or vectors. It does not process row by row. It processes a chunk of data, which you may call that as a batch. Do not interpret this batch as saying that we are doing operations in batch. No. Instead of, it is blazing fast, it is optimized to operate at real time. But instead of reading one row at a time and operating on it, it is picking up a batch of rows and operating on that. There are some modern CPU level advantages that Photon has. For example, it uses SIMD instruction. What is SIMD? It is single instruction multiple data. So to achieve parallel operations, it uses the model of single instruction multiple data. It has better cache locality. It can keep hot data in L1, L2 CPU cache. So when we studied operating systems in our college, we would have studied about all these L1, L2 caches that a CPU has. When we learnt about our operating systems, we learnt about CPUs, we have heard about these caches, right? They can be used to minimize any kind of expensive memory fetches. So these are at a CPU level, these improvisations. Apart from removing the JVM dependency and having a vectorized execution, it also gives advantages at CPU level. Okay. Also, Photon can seamlessly plug into Spark's catalyst optimizer pipeline. So it doesn't mean that with Photon coming in, we have to rewrite the queries that were earlier written. No, Photon can be just enabled by a configuration, and Photon and Catalyst optimizer can work hand in hand together. So Catalyst will optimize like it was doing, and Photon will give that extra benefit of by removing all the overheads that earlier were there with the JVM bottlenecks. What is the real world impact? When we use Photon, what is the impact? So there have been some benchmarks that people have done, and it shows that at least 3x faster performance is achieved when we use Photon. And this is primarily observed obviously when we have join heavy queries, aggregations, analytical workloads, because for simple queries it may not matter that much. But when there are complex join conditions, aggregations, it will really help. Photon will also reduce the infrastructure cost because it is lowering the overall compute time. So the moment the compute time goes down, the infra cost will also go down. And there have been people who have used Photon and they have said that it is giving them performance boost in terms of doing real-time analytics, in terms of improved developer productivity, because optimizations are automatically done. They were earlier done by Catalyst optimizer, but now it is a multi-fold optimization. So it is giving developer efficiency and productivity. It is faster in terms of all the complex data lakehouse queries. So that's the impact of Photon. Now, one more thing that we need to keep in mind is that with Catalyst, when Catalyst was introduced by Spark, keeping in mind the Spark SQL queries, it kept on improving Catalyst. So Photon has been introduced, but they have not stopped improvising on Catalyst optimizer. So the Catalyst optimizer's role has been extended. Initially, it was built for query optimization, like doing predicate push down, column pruning, join reordering. These were the common things done by Catalyst. But now it is becoming even more smarter in terms of planning, because it can analyze the workload, what kind of workload it is, what kind of resource availability is there, and what are the runtime statistics. Based on that, it optimizes again. So it is like a brain of the Spark SQL. It ensures that the execution is efficient and adaptable. So earlier it was only operating at the level where it was optimizing the query before execution, but now Catalyst optimizer can collect runtime stats and improvise. So it is also getting smarter and smarter. So you have heard about adaptive query execution, right? The adaptive query execution is also a way of getting performance efficiency. How? There is often skewness in data, which means our data is partitioned, but the partitions are not equal. Some partitions are very small, some are large. So data is skewed. In those cases, whatever static plans that get created before execution, they won't know, right? They won't know that at runtime the data is skewed. Some partitions are uneven. So when Catalyst optimizer was designed to only optimize the plan before execution, it will not know about skewness. It would not be able to dynamically adjust based on runtime stats. That's where adaptive query execution was introduced, which can dynamically adjust the execution strategies because it will look at the data and know that the data is skewed. And how will it optimize? How will it adjust the execution strategy? Is it can do dynamic partition pruning, which means Pruning is just like we cut a tree. We say we are pruning it. It's just like that. We are removing or cutting out on all unnecessary partitions which are not required. So at the runtime, it can assess which partitions are unnecessary and we don't need to scan them. It can handle skew joins. So it can automatically detect and split large partitions. What will happen if we have a very huge partition and the others are small, which is a skew case, right? The job will only complete when all the tasks complete. So if a task is operating on a huge amount of data or a bigger partition, that task will become a straggler, which means that is the task which is the bottleneck and taking most of the time. The job will only complete when all the tasks complete. If the data is skewed, the smaller task will complete quickly, but you will still have to wait because the big task is still going on. So these are called stragglers, and this happens when there is a skew in the data. So these kind of detection and how to optimize that join can also be done by adaptive query execution. At the runtime, it switches join strategies. If at the before execution it had decided to do a shuffle join, at the time of running the query, it may realize that the data is smaller than expected. We don't need a shuffle join. Let's do a broadcast join. So this is giving us a real-time efficiency. So it is very important to have optimizations before execution to create a better plan and choose a better physical plan. At the same time, it is extremely important to do a runtime optimization, which was introduced by bringing in adaptive query execution. Now, how will Photon and Catalyst work together? They need to work together. So Photon is the decision maker. The Catalyst decides when and how to hand off the execution. What does that mean? If a query is CPU intensive, then it is better to have a vectorized execution, which means that Catalyst will send the query to be executed by Photon, because Photon doesn't do row by row execution. It does a batch or vector based execution. So whenever Catalyst sees that it is CPU intensive, it will pass it on to Photon. Where there is less CPU intensive work or simpler operation, then Spark JVM execution path should be sufficient. There would be no JVM overhead. So this kind of decision making has to be done in conjunction with Catalyst and Photon. They are doing it amongst themselves. This dynamic orchestration will ensure that Spark workloads are always getting best of both the worlds. So Catalyst can do a very good intelligent planning. Photon can do hardware optimized execution. So it is like using best of both the worlds. The Photon and the Catalyst optimizer are working hand in hand and deciding who should be taking over the execution, whether Photon should take it or Catalyst should do the planning. So think of it this way: Catalyst is for doing intelligent planning before execution, Photon is to do hardware optimized execution. Now in future, what will happen? We saw what is the advantage or where Photon is good versus where Catalyst is good. In future, what will happen? In future, there will be a deep integration. Catalyst is like a brain who will do the planning, and Photon is the muscle because it will do the execution. So like I said, Catalyst is the intelligence who will analyze, apply optimization, adapt in the runtime. So Catalyst is doing optimization at both the phases, right? During compile time and during runtime by using AQE, adaptive query execution. And when Catalyst decides that okay, this is a complicated job, requires CPU intensive work, it will give it to Photon, which has the execution power because it does not have the JVM overhead. It is using a C++ native engine and operating on vectorized hardware aware. It is also hardware aware, so it gives you a lot of speed. Together they form a closed feedback loop, which means when Catalyst and Photon work together, Catalyst generates the plan, Photon executes it with maximum efficiency, and whatever stats it collects, it gives it back to the Catalyst, which will further refine it. So it's like a loop between the two: the planning, the execution, feedback to the Catalyst, and improvisation of the plan. Again execution, again feeding the feedback. So it's a closed feedback loop running between Catalyst and Photon. And what are the new capabilities? So definitely Photon has very good speed in terms of execution. But what else? What are the other new capabilities? One is vectorized processing. We saw that it is doing execution in batches to maximize CPU efficiency. It can do advanced push down optimization. So when we are talking about both of them working together, Photon will do batch pickup or vectorized processing. Advanced optimization, like doing more operations into the Photon's native execution, can be done by Catalyst. The Catalyst understands that these are advanced optimizations which a Photon can do. There will be seamless SQL and data frame acceleration. Users don't need to change the code. The integration will automatically apply. So it's not that if you've written the code when Catalyst was available and now with Photon, there is some code level change. No, there is a seamless handshake between Catalyst and Photon at execution level. And this reduces infra cost. Why? Because Photon is working on L1, L2 caches of the CPU. It is utilizing that and it is reducing the compute time. So definitely the cost of infra goes down. So all in all, both Catalyst Optimizer and Photon are working hand in hand. Okay. What are the future implications with both of these together? There can be multiple complex workloads about it can be ML feature engineering, it can be business intelligence, streaming analytics, or any kind of use case that can be supported by both of these. It is very close to data warehousing performance, because earlier when we had data warehouses, they had MPP architecture. The databases were MPP. Now with Spark and these capabilities optimization, Spark can be very competitive to those MPP architectures. But at the same time, it has flexibility to operate for all kind of scenarios: streaming, ML, batch, real time. And these kind of hardware accelerations that are happening, these are foundations for our future next gen optimizations. So the Spark ecosystem is becoming faster, smarter, leaner, and future proof. So Spark or Databricks is coming up with a lot of optimizations so that the developers' productivity is increased and the time that the developer spends in doing optimization can be reduced. But when we have all these advantages, there are still some best practices that we should keep in mind. First of all, we have to enable Photon where it is available. Whenever we know it is a data frame heavy job, a SQL heavy job, we should enable Photon. We should design queries with Catalyst in mind. We should not introduce unnecessary complexity. See, it's a shared responsibility. The developer writes better code, keeping in mind what should I do? Should I filter data first? Instead of doing a lot of data shuffle across the network, and those kind of decisions, and help Catalyst to optimize predicate push down and other things. We should understand how adaptive query execution reshapes the query in real time and fine tune partitions. Of course, AQE or adaptive query execution will come into picture when the code runs, but from our side we should be designing the partitions well and not have skewed partitions. And we should always monitor the jobs thoroughly to see a detailed analysis of the logs from the Spark UI we can do to see how we can benchmark and fine tune our jobs. And we can always do a comparison between Photon versus JVM execution. What is better for our particular job? Because each job is different and it depends on what we are doing in that Spark job and what to choose. Okay. Then the last we come to upcoming features and roadmap predictions. What will happen is we now have Photon, but Photon will have deeper integrations. It will cover both Spark operators, not just data frame, but other Spark operators too. AQE will get enhanced and have more intelligence, which can do smarter skew detection, because this space is evolving constantly. There are new challenges, new limitations that get discovered. So Spark is also keeping up with all these changes and improvising constantly. When we increase or fine tune the way the optimizers work, the execution work, engines work, at the same time hardware acceleration is needed. like what kind of processor we use. Are we using FPGAs for specialized workloads? Are we using GPUs? Even hardware plays a big role. So it is a combination of hardware optimization versus and execution engine or optimizer betterment. And since the world is moving toward a lake house kind of a use case where you want to have best of both the worlds of big data as well as data warehouse, so definitely there will be tighter optimizations with formats which are native to this lake house execution. So I hope this has given you a good overview of what are the bottlenecks that Spark had and what is the role of a catalyst optimizer versus Photon and how they can work together for the betterment of the uh, developers' time, how to save developers' time and how to optimize the jobs better. So please like, share, and subscribe to the channel and keep watching for next interesting videos. Thank you so much.